Everybody likes geometry. So let's do it. So let's talk about, for now, let's talk about the geometry. It's not a good marker. Of 1 qubit. Okay, so we got really sophisticated in this course. We did a lot of stuff, and like now we're like these algorithms that operate on like n qubits and Hadamard transforms and stuff. And now we're going to go back to 1 qubit for like some time. And we'll eventually get up to 2 qubits like in the next couple weeks. So what's up with 1 qubit? Well, you probably got a hint of this from the homework. You know, whenever we have the state of 1 qubit, like we write its state in this like honestly extremely like verbose phraseology. We're like, oh, its state could be like x amplitude on basic state 0 and like y amplitude on basic state 1, where x and y are real numbers that satisfy x squared plus y squared equals 1. Okay? And finally, like starting today, we're going to be like, this is too verbose. Come on. It's like, let's just write x and y. So henceforth, we will denote this state just by listing the amplitudes in a list, a vertical list of height 2, also known as a vector. So that's how we're going to, so henceforth, like this vector denotes this state. Okay, so you can always remember, like this is the 0 row and this is the 1 row. And moreover, what does this mean? It means, okay, the x squared plus y squared, that's the, by Pythagorean theorem, that's the square of the length of the vector. So this is the square of the length of the vector. So this sum of squares of amplitudes that we've talked about so much has a geometric meaning. And you know, this means that the squared length of the vector is 1, which means that the length of this vector is always 1. And for like this class and for a while, I'm going to go back to only talking about normalized states. Okay? So for the most part. Good. So you know, every state is a length 1 vector. This is sometimes also called a unit vector. And that's very enjoyable, right? So it means that like you can draw all possible states on like a nice 2-dimensional picture. So here are all the length 1 vectors. They all lie on this circle. So all the points or vectors on this circle are the possible states of a qubit with real amplitudes. Okay. Now, one thing that we also got used to was in the special case that like the state was, let's say, the basic state 0, we normally didn't like write out like, oh, this is 1 amplitude on 0 and 0 amplitude on 1. We kind of got used to like abbreviations. So we have these abbreviations. You know, we just write this for 1 amplitude on 0 and 0 amplitude on 1. But now, you know, we decided to write this just as like a column vector, 1, 0. Okay, and that's this one right here. I mean, this is the point 1, 0, as you know. 1, 0. So like this vector is 1, 0. And like we got used to just calling it by this symbol. So that's what we're going to do. So like this vector has like a special name, and we call it, well, 0 in these angle brackets. And similarly, we have like a, you know, the really long form version of this name is like 0 amplitude on this basic state 0 and 1 amplitude on basic state 1. But now we're just calling this like 0, 1. That's the, you know, that's the vertical vector. This is 0, 1. Okay, and we're just going to call this basic state 1 in angle brackets. Okay, and you know, this should warm your heart from like remembering like basic geometry or like vectors or whatever. Like these are the 2 standard basis vectors. And now they have these like pleasant names, these short names. You know, I guess like when you're in like high school or whatever, they call this like I vector and this one like J vector maybe. But like now we're like cooler. We're going to call them like 0 and 1 in angle brackets. And you know, similarly, if you have like a general state with x amplitude on 0 and y amplitude on 1, you know, in high school or whatever, they're like, okay, this is like x, a scalar, times like 1, 0, plus y, a scalar, times 0, 1. And so now we can write this as like x times this vector plus y times this vector. Okay. And henceforth also, like this will be very common notation as well. So this is, okay, we're going to stop writing out this phrase, and we'll think of it as a vector. But like this is also a vector, but this is like using, you know, basic linear algebra rules. I'm doing a scalar times a vector plus another scalar times a vector, and that's a vector. Okay, so, you know, like an example of like these very common states I'm always like talking about, like this one maybe is 0.6, 0.8, 0.6. Okay, that's like a basic qubit state, which we'll sometimes also write as, you know, 0.8, 0 plus 0.6, 1. You know, it's a 0.8 of this guy plus 0.6 of that guy. And we won't talk about it today, but like, let me remind you that whenever you have a qubit, right, a qubit is like a mathematical concept, and it's described, you know, state is now described by like a point on this circle. But it's also supposed to represent the actual state of a physical object. And especially when you're studying like the geometry of one qubit, like my favorite such physical object is the photon. We talked about this in lecture 1 or 2, maybe. Like a photon has this property called polarization. It's like affected by your polarizing sunglasses or whatever. And it's pretty correct to sort of think about it as like the direction in which the photon is wiggling. So like imagine a photon coming right at you. Here it goes. If it's horizontally polarized, it means it's like wiggling like this as it's going. And if it's vertically polarized, it means it's like wiggling like this as it's going. And you know, if it's like state now is like 0.8, 0.6, you have this like geometric picture where this is like an actual line. It means it's like wiggling. Can't do it. It's like wiggling like this as it's coming at you. Okay, and with like this mental perspective, you're like, oh, it's not so weird to think that it's, you know, in a superposition of 0.8 on 0 and 0.6 on 1. Like that seems fine. And yeah, it is fine. So this is like a nice geometric thing to keep in mind when you're thinking about physical qubits. Okay. Now this is all for one qubit. Now let me say, all of this generalizes naturally to when you have more than one qubit. Okay, so more generally, if you have, let's say, 2 qubits, you know, we saw that like a 2-qubit state is like, you know, we used to write it laboriously as like x amplitude on the basic state 0, 0, and like y amplitude on the basic state 0, 1, and z amplitude on the basic state 1, 0, and w amplitude on the basic state 1, 1. And we had this normalization rule that, you know, x squared plus y squared plus z squared plus w squared equals 1. Okay? And yeah, so similarly, henceforth, we're going to write such a state, if we ever encounter it, as like a column vector with 4 entries x, y, z, and w. So again, sort of henceforth, we're going to abbreviate this as, you know, x, y, z, w. This is like a vector in 4 dimensions. And again, like, you know, the Pythagorean theorem in 4 dimensions is like x squared plus y squared plus z squared plus w squared is like the squared length of this vector. And if the squared length is 1, that means the length itself is 1. And so again, this is like a unit vector, a length 1 vector. Okay, so similarly, if you have 2 qubits, then like every possible state is just like a length 1 vector in 4 dimensions. Now there's like this great sadness in life, which is that, you know, humans can visualize up to 3 dimensions. And after 4 dimensions, you cannot visualize it. And like, so like 1 qubit is 2 dimensions. Great, lovely pictures. 2 qubits is already beyond our power to visualize, which is sad. Even if we could just like get 1 more dimension, it'd be good. Because like 2 qubits is where stuff really starts to get interesting. You can have entanglement and so forth, but we're stuck. So you just got to use your imagination. That's all I can say. Like, just when we start talking about vectors in high dimensions, just like use your imagination and constantly make an analogy to like vectors in 2 and 3 dimensions. And this will get you pretty far. And then otherwise, you just have to fall back on thinking of like, all right, a vector is like a list of numbers. Like, what can I do besides that? Now, yeah, let's get this guy out. So similarly to the 1-qubit case, in a special case where like x is 1 and all y, z, and w are 0, so you have like all the amplitude on basic state 0, 0, we just like called this such a state 0, 0. And we'll do the same thing here. So like sort of similarly, we have this like notation where this symbol, 0, 0 in the angle brackets means this vector, 1, 0, 0, 0. And 0, 1 means this vector, 0, 1, 0, 0, and so forth. Okay, so we always like order our entries in like the natural like base 2 counting order. So the 0th, 1st, 2nd, and 3rd entries. Okay, and so now when you actually see the symbol, like you can really think of it as just like a name for these 4 column vectors. So now we have like nice names for the 4 standard basis vectors in 4 dimensions. Whenever I talk about geometry, like I always do this. Like somehow to me in my mind, like this is like a picture of like the 3 standard basis vectors in 3 dimensions. And I'll still show this even if it's like there's supposed to be 4 dimensions because this is all we can do. Okay. You know, and similarly to how they, teach you at the very beginning of linear algebra that like, any vector in 4 dimensions is like some scalar times the first standard basis vector plus another scalar times the second standard basis vector, et cetera. Same situation here. So like this can be written as x, a scalar times, this vector, which we're now calling 0, 0, plus y, which is a scalar times this, plus z times this, plus w times 1, 1. Okay, so this is a very common way to write the state of 2 qubits. And like you should think in mind, this is like some linear algebra notation. Scalar times a vector plus, et cetera. And this is like addition of vectors. Okay, so similarly, if you have 3 qubits, then you'll have vectors in 8 dimensions. So a state will be like a length 1 vector in 8 dimensions. And like the first standard basis vector will be named 0, 0, 0 in angle brackets and so forth. Any questions? Let's pass this out. We're going to get it today. It's 1 in 4 chance today, but it's going to be good. Oh, sorry. We're going to hit it. I know it. Okay, let me now have a short aside on these crazy brackets, because like maybe they've been bothering you for like the whole course, and you're like, it's asymmetric. Why do we have this like bizarre brackets? All these like angle brackets are part of something called Dirac. This is like some old physicist. Ket notation. So what is Dirac Ket notation? It's just this. Here's the whole, well, it's not all of this, but it's basically this. When you see these like asymmetric brackets, this signifies theta type equals column vector. Okay, that's exactly what it means. So, for example, if you're using Dirac's, and like somehow a column vector is also called a ket in Dirac's world. For some like dumb pun reason that maybe I'll mention later. But at least column vector is like 4 syllables and ket is 1 syllable, so that's nice. So indeed, like, in like linear algebra textbooks, they're always talking about like they ought to vector v. But then they're like, if I just put v, it'll look like a scalar maybe. So they're like, how can we decorate this so that the reader will know it's a vector? And like some linear algebra books like make it boldface, which is like the worst possible idea. I hate that so much. Another thing that they'll do, well, they'll put like a little arrow above it, and like that signifies to you, oh, the data type of V is column vector. This notation is fine. I don't hate it that much. But like, this is the real good notation, in my opinion. You just put it in these like asymmetric brackets, and that's like signifies to you, oh, this object is a column vector whose name is V. And you might be like, why is it going on and on? Like, why do we need like new notation? Like, what is so, why? It turns out it's great. You're going to love it by the end of the course. It looks dumb, but like you really made it an ingenious choice with this notation. In fact, another thing is like this notation is very like synonymous with quantum computing or quantum mechanics. Like you like see this notation when you're reading quantum books, or like when you read quantum books, so you like see this notation. This notation has nothing to do with quantum. Absolutely zero. This is like a notation purely for linear algebra, which of course quantum mechanics uses. But it's just a linear algebra notation. In fact, I love it so much that when I do like linear algebra for my own like fun and enjoyment and research, even if it has nothing to do with quantum, I use this notation because it's really great. We'll see a bit later a little bit more to this notation and what makes it extra good. But yeah, that's another thing. Like I think I've managed to not do it in the course so far. But like, it's very common to call this object ket0. It's like the column vector whose name is 0. And it's like very common to call this object ket1, the column vector whose name is 1. So we'll probably start doing that. But ket means column vector.